Today's video will demonstrate how to use the set to implement the binary sort. Hello, I'm James Helfrich. There are many sorts. There's the insertion sort, the merge sort, the quick sort, and all these have different performance properties, and some of them are rather complicated to implement. However, the binary sort is actually really easy to implement and very efficient, and we do that with a set. First, let's remember what a sort is. A sort is a function that takes an unordered collection of elements and sorts them in either ascending or descending order. In this case, I have a collection of 8 numbers, and I will sort them by putting in ascending order. And how I know it's ascending? Because I will use the less than operator. There's a large number of different sorting algorithms. There's the bubble sort, the insertion sort, the selection sort. These are all n squared algorithms. There's the merge sort, the quick sort, and the binary sort. These are n log n. Today, we're going to learn how the binary sort algorithm works. To see how this works, we're going to start with a collection of different elements, and I'm going to put them into a binary search tree. H goes in the top, and then D goes to the left, and L goes to the right, and N goes to the right of the L, and then F goes to the left of H and to the right of D, and then J goes to the right of H and to the left of L, and then B, and then A, and then G and C and M and E. And I'm iterating through the collection of unsorted elements, and I'm building a binary search tree, which remember is the underlying data structure for the set. And then from here, I'm going to put them in sorted order by iterating through the binary search tree. I'm going to start with begin. I'm going to go all the way to end, and this is going to be in the left visit right order, otherwise known as ascending order. So A is going to go, and then B, and then C, and D, and E, and F, and G, and H, and so on. As I progress through the tree, I'm going to rebuild my array of elements. Okay, let's take a look at the pseudocode of this binary sort. So I'm going to take a collection of elements called data and the number of elements, and I'm going to create a binary search tree that is right now empty. And I'm going to walk through all the elements of my data collection, and I'm going to insert them one at a time into my BST. When I'm finished, my BST will contain all the elements, and remember, BST maintains sorted order. The last thing I'm going to do is I'm going to iterate through my BST from the beginning to the end. I'm going to put each element back into my data collection. Now, I can do this much easier with a set. What I'm going to do is I'm going to create a multi-set and fill in it with all the elements from the data from the beginning to the end. And now my multi-set will be filled. And then I'm going to traverse my multi-set from the beginning to the end. And every element I have, I'm going to push back into my data vector. So these two pseudocodes are exactly the same, but the multi-set makes it a little bit easier to see. Okay, let's take a look at how this binary sort works. Now, first of all, I'm going to start with a vector of ints. And I'm going to call it V for lack of anything better. And I'm going to fill it with some values. I'll use the initializer list 4, 7, 2, 3, 1, 6, 9, let's say. Just a bunch of random numbers here. And then I'm going to say set of int, set, and here I'm going to use the set's iterator constructor. So from v.begin to v.end. Now remember, the set is implemented as a binary search tree, so this will fill the set or the binary search tree with all these values from the vector. Then I'm going to say vector.clear, remove all the elements from the vector. Then I'm going to say for auto by reference element in my set, for every element in the set, then I'm going to v.push back my element. And that's going to put everything back into the set. All right, let's set a breakpoint here, and let's see how everything works. Build succeeded, awesome. And when I run the code, we'll see my vector is now 1, 2, 3, 4, 6, 7, 9. It works exactly as I expected. That's awesome. But what happens if I say 1, 1, 1, 1, 1? Remember, what set does is it makes sure there's only unique elements. So when I run this, I'm not going to get it sorted the way I expect because I'm only going to have one copy of 1 when I used to have several. So instead, I'm going to have to use the multi-set, and the multi-set behaves exactly as set except without the uniqueness constraint. When I run this again, then it's going to say 1, 1, 1, 1, 1, 2, 3, 4, 6, 7, and 9. So it sorts correctly. That's awesome. Okay, what I want to do is put this into a function, and I'm going to call this function binary sort. And what I'm going to do is I'm going to first create a multi-set. This does all the work. And then I'm going to clear out the elements. And finally, I'm going to put the elements back in our vector. All right. All right, let's see if this works here. So I'm going to say vector, and I'm going to say binary sort and v. Okay, let's see if that works the same. Oops, haha, I used the wrong name here. My bad. I do that from time to time. Okay, let's run that again. There we go, Bill succeeded, awesome. Look at my values, it works the way I expect. That's cool. This is helpful, but I would like to make sure that it works for really vectors of any size. So I've created a little function that I call randomize, and randomize will take in a vector of integers, and it will clear everything out, reserve it, and then fill it with a whole bunch of numbers between 1, 0, and 100,000. So I'm going to call vector, and I'll say randomize v, and let's do 100 elements in there just for fun. Okay, when I run this, then sure enough, everything is in sorted order. So my binary sort works, and it's remarkably efficient and clean, isn't it? Well, it's efficient in terms of lines of code, but my question is, how efficient is it with regards to algorithmic efficiency? Well, in order to figure that out, I need to create a SPI. Now, my SPI is a double which counts the number of times it's been used. So now my randomize function is going to have a SPI version of this as well, and it's going to create a value between 1 and 100,000, just like with integers, except this is also going to allow me to keep track of how it's used. And in order to keep track of how it's used, I have a report function which will tell me how many times the default constructor was called, the copy constructor, the assignment operator, the move assignment operator, and all those other things, okay? So now I will report and how I did. And so when I run this, build failed, oops, my bad, haha, vector, this is not a vector of ints, it's a vector of t, multi-set of t's. So made a mistake there. All right, so now my copy constructor got 200 times, my move constructor got called 100 times, a lesson number got called 617 times. Well, why did my move constructor get called? And that's because of my randomize function here. So what I really need to do here is I need to reset my SPI. And let's do 1024 just for fun. All right, and when I run this for 1024 times, then the copy constructor got called 2048 times. In other words, for every element in the vector, a copy constructor wants to put it into the binary search tree and one to take it out. And my lesson operator called 9,962 times. All right, if I double the size of this to 2048 and run this again, then the copy constructor got called 2 times for every element, and now 22,000 times the lesson operator got called. 2048, how about 4,096? Let's run that again. And how about 8,192? Okay, let's see how efficient my binary sort is. Remember, I claim it to be n log n, but we're going to graph it to see how many times the copy constructor got called and how many times the lesson operator got called. And that will tell us the true algorithmic efficiency of the binary sort. First of all, how many times do I have to copy elements? And it turns out for every element, I'm going to copy it twice, once to put into the binary tree and once to take out. So this is going to be O sub n exactly. How many times do I call the lesson operator? Well, boy, this also looks very linear, but it turns out it's not exactly O sub n. I'm going to look at the same thing again. So here's a bunch of data I created with a set of size 1, set of size 2, 4, 8, 16, 32, 64, and so on. So how many times does less than get called? Well, it's going to get called n log n. Let's take a look at 1024. So n would be 1024, and log n would be 10. So 10 times 1024 is approximately 10,000. And look, it was 9,962 times. Let's look at 2048. N is 2048. Log n is 11 because log of 2048 is 11. So 11 times 2048 is approximately 22,000. And this is true for all the numbers. When I graph it, we'll see once again it looks very linear, but there's a curve towards the bottom, almost imperceptible. And that's the key characteristic of n log n, because it's mostly linear, except when the n is very small, you can see a slight curve to it. But as n gets large, it looks very linear. You can learn more about the binary search tree in the binary search tree chapter, and you can learn more about the set in the set chapter of the C++ data structures textbook.